Hello students, this is Dr. B and we are going to run activity 3 in the plate tectonics module. I'm on learn.concord.org. That's learn.concord.org, and you have an account and you can either log in with Google or with Schoology and then find Dr. B's physical science class and run by myself. We are going to go to activity 3 here. We did 1 and 2 already. We're going to work on Earth's plate system here. In activity 2, we investigated places on Earth where mountains are formed as two plates are moving towards each other and one goes under the other. So if you want to model that with your hands, it's the ocean plate diving under the continental plate. The continental plate crumples and makes some mountains, and we can think of the deep trench that happens between the mountains and the ocean plate as this kind of gap right here. Scientists call this process subduction. As you saw, the subduction of one plate beneath the other creates landforms like mountains and trenches and events like earthquakes and volcanic eruptions. It's important to remember that Earth is not made up of just two plates, but many plates, all of them moving at the same time, but in different directions. In activity 2, you looked in detail at what happens when two plates are moving towards each other. However, all plates can't be moving towards each other, and every plate has other edges. So we have to think of if two plates are moving towards each other here, they're probably moving away from, think about my wrists, are probably moving away from other plates. So one edge is doing a convergent boundary, and the other edge is probably doing a divergent boundary. Since Earth is made up of lots of plates, it must be true that each plate touches all the other plates around it, and there must be different ways for plates to interact at these different kinds of boundaries. In this activity, you'll investigate earthquakes and volcanoes in various places that are different from the Andes and Aleutians to explore the landforms and events associated with other types of plates interactions on Earth. Let's investigate the volcano data to see we can find the rest of the boundaries of the plate on which South America sits. Then we can find out what's happening with those other boundaries. So let's put data, earthquakes, and volcanic eruptions, even those prior. And let's run here. I see some plate boundaries developing here with these lines of earthquakes and volcanoes. Using the earthquake and volcano data to see if you can outline the entire plate that South America is part of. So if we take a snapshot here, we can use our pen tool. I'm going to click white here, click on the pen, and I'm going to trace that boundary along South America here and then go over to the Midocean Ridge and then some volcanoes. So that looks like the South American plate to me. I used all of the boundaries here, all of the earthquake and volcanic data to outline the boundaries. So you can do the same thing in your own Concord. What evidence did we use from Tectonic Explorer to locate the boundaries? Well, I used earthquakes and volcanoes. Volcanoes are where magma is coming up, and that's a sign that there's seismic activity or there's movement between the plates. I'm going to hit next at the lower, just out of the screenshot range here. What's happening along the boundary in the Atlantic Ocean? Now that you've sketched an outline of the plate that includes the South American continent, we need to investigate other boundaries of this plate. Part of the outline of this plate is right down the middle of the Atlantic Ocean. We saw that with the earthquake data. Just like we did before, we'll investigate the seafloor surface features, the topography, as well as earthquakes and volcanoes to try to understand what's happening at this plate boundary here. So let's make a cross-section of the earthquakes on the boundary of the plate in the Atlantic Ocean. Remember to draw your cross-section perpendicular to the line of earthquakes. So unfortunately, iPads can't do this, and I'll do this for you, and you can take a screenshot of it. So I will go data type here. I will put my earthquakes, put volcanic eruptions. I'll let it run. That way I know where the Midocean Ridge is. You can see right here down the middle of the Atlantic, there's a nice Midocean Ridge. I can draw my cross section right perpendicular to that. So I'm going to draw cross section, draw it at 90 degrees. And I'm going to open the 3D view. I can see the depth of the earthquakes here, and it seems like they're pretty shallow at this Midocean Ridge. So I'll take a snapshot. And if we look at the key here, all the earthquakes seem to be red, which is a depth of 0 to 30 kilometers. So that's pretty shallow compared to some of the earthquakes that were happening at the convergent boundary between the Nazca Plate and the Andes right here. They were getting very deep earthquakes. At the Midocean Ridge here, we're getting very shallow earthquakes. So the depth of the earthquakes along the boundary in the Atlantic Ocean is very shallow. And plates are spreading apart. Lava is just coming up between those plates and spreading them apart. There's no plate subducting. So that might be a clue about what's happening here. Below is a geographic profile that it provides information about the land elevation along the profile line from point A to point B, so point 1 to point 2 here, across the Atlantic Ocean. So this is a cross-section of the Mid-Atlantic Ridge. We can see you leave the South American continent, it gets very deep. Well, that's the ocean, that makes sense. It gets less deep in the Mid-Atlantic. There's kind of like a little mini mountain range here, and then it gets more deep before you head over to Africa. Mid-ocean ridges are the longest chain of volcanic mountains on Earth. The ridges look like mountains that run along most of the ocean floor. The geographic profile is drawn across a mid-ocean ridge. Based on the geographic profile, where is the ridge the highest, making the Atlantic Ocean the shallowest? Well, let's go look. Looks like around in here, and you'd read the distance in kilometers on the x-axis here. Moving from the high point of the land in the ocean, the shallowest water, towards either continent, what happens to the land? So we're looking right here. If we start in the shallowest place and we move towards land, it looks like it's going to get deeper. We're kind of going down the mountain range, and it gets deeper before we go up the continental plate here. So I'll let you pick your question from number 6. Looks like it goes down, it gets deeper, and then it goes up pretty quick when you get to the There's a next button just out of the range of the screenshot. I'm going to click that and go to our next adventure here. The video slideshow is an introduction to what happens at divergent boundaries, the type of boundary that has a mid-ocean ridge like the eastern edge of the South American plate. Watch the video and then use the Tectonic Explorer to make a model of the entire South American plate. So you get to watch this video on your own. I'll hit next. Let's model the South American plate. Scientists have named Earth's major plates The name of the plate on which South America is located is called the South American Plate. You'll continue to investigate the other edges of this plate, in particular what happens to the other side of the plate from the Andes Mountains in the middle of the Atlantic Ocean. Tectonic Explorer has been set up to simulate a boundary that is like the South American Plate boundary underneath the Atlantic Ocean. A cross-section has already been drawn so you can focus what happens beneath the surface. The model also shows where earthquakes and volcanic eruptions would happen along this kind of boundary. Note that the earthquakes and volcanic eruptions happen very quickly compared to how fast plates move. The earthquakes and volcanic eruptions in the model are included to show you where the earthquakes and volcanic eruptions would happen during the process of plate movement. Okay, let's hit play and see what happens here. So it looks like these plates are spreading apart, but there's never like a hole between the plates. There's magma that's always coming up and taking that space. That hot magma, that melted Earth's mantle that's less dense, is rising to fill in that space there. So run the model, take a snapshot. It includes the cross-section, draw arrows to show the direction the plates are moving. All right, let's do that. Now this is a divergent plate boundary. No plate, one plate is not running into the other plate and making mountains. These plates are spreading apart. So your arrows that you draw, you can pick a color here, need to reflect that the plates are spreading apart. And I'm sure you can figure out how to draw in those arrows that show which way the plates are heading. Describe the landforms and events you see at the boundary here. Well, I see two plates. I see hot magma rising to take this space as the two plates diverge. I see the plates moving in opposite directions because that's the definition of a divergent boundary. I see, if you zoom in here on the plates here, I see a mid-ocean ridge forming, so like a mini mountain range in the middle of the ocean. There's an occasional volcano or earthquake going on there. So those are some hints that you can write down for question number 8. There's a lot to see. Plates are moving apart, there's movement of magma, there's a mid-ocean ridge, there's earthquakes, volcanoes, there's tons of seismic activity. It's pretty cool, pretty dynamic. Notice in the model, molten rock, magma, rises up from the mantle, solid rock is shown green, to fill in the space that forms as the plates move. This magma cools to form new plate material and forms the mountains that are the mid-ocean ridge. Let's reset the model and rotate the planet so that you're looking in the boundary on the other side, the boundary that forms the mountains like the Andes Mountains. Make a cross-section of the boundary that forms the mountains. Okay, so we need to rotate our plate. Oops, need to rotate it here. So let's see, where is it crashing into another? So that's divergent. Let's see, it looks like there's a convergent plate here. So this is there we go. So it's divergent here and it's convergent here. So we want to draw a cross section over this convergent part of the plate. There we go. So make a cross section of the boundary that forms the mountains. We just did that. So we're getting the idea that if plates are diverging in one place, they're converging on the other side of the plate. So this plate here It's diverging here and it's converging here. So that plate is moving to the right on this particular frame of reference. So it's moving away from this plate here, and it's moving into this plate here with the continent on it. And you can see the mound building going on here. That gives us a hint, and you can see the mound building in the cross section as well. That gives you a hint that there's a convergent boundary there. So if it's moving away on one side, it's moving into another plate on the other side, and you can describe what you saw on the model here. This looks like a convergent boundary to me. We have some mountains, we have one plate subducting or going underneath the other one. In the middle of the Atlantic Ocean, there's a Midocean Ridge. The tallest part of the ridge is 2,500 meters higher than the rest of the seafloor. Take a snapshot of the profile of the Atlantic Ocean. Where do you think the plate boundary is located on the profile? Put an X on the profile where you think the plate boundary exists. So we just have to go take a snapshot here. And you need to fill in an X here, somewhere where you think the boundary between the plates, where are they coming apart? You can click this to choose a color. You can choose the pen, and somewhere in here, you can draw an X to show me where the boundary is. Why did you put your X where you did? You might want to go back up to Seismic Explorer if you need some help here. Or you can go back to Seismic Explorer where you have the map, and you can look for earthquakes and volcanoes that will help you figure out where those plates are diverging in the middle of the ocean. Seismic Explorer is the one where all the little dots for earthquakes and all the triangles for volcanoes come up, and you can go back a few activities to find that. I'm going to hit the next button at the bottom of the screen. Doesn't show up on the screenshot. So I will play this one. It's short. Midocean ridges are formed where two plates are moving away from each other. The Midocean Ridge extends for over 56,000 kilometers under the oceans. Scientists have mapped Midocean ridges and sent submersible vehicles to those areas to collect samples and see what mid-ocean ridges look like. And they look a lot like this. In the video below, you can see a map that scientists made of a mid-ocean ridge in the East Pacific Ocean near California. You can see that the plate boundary is marked by a valley. So in the middle of where we're looking here, this valley here, is where the two plates are coming apart. And we continue to kind of fly down this valley here in this computer simulation. You can see that that valley isn't really that deep. There's constant movement of magma up from within the mantle. There's hot, warm rock rising into that boundary, and so there's no big hole in the earth. It's constantly filled by warm rock rising up from beneath in the mantle. Valleys are present on all ocean ridges. The valleys along the mid-ocean ridges can be as deep as 1 kilometer. In comparison, ocean trenches, which are found where plates are moving towards each other, are much deeper, plunging 3 to 4 kilometers deeper than the surrounding ocean floor. So here's the trench where there's a convergent boundary. The ocean plate is subducting underneath South America here. And the names of the folks who did this map keep popping up to give them credit. So this is where a convergent plate is. That's a trench. This is where a divergent plate is. And that valley you can see is much smaller than the trench. So divergent plates don't have giant holes between them. They're easily filled by magma, which I guess, turns into lava as soon as it comes out on the crust. The valley is where the majority of volcanic activity occurs along the Midocean Ridge. As two plates separate, the solid mantle injects magma, molten rock, along the ridge. The magma is super hot, that's 700 to 1300 degrees Celsius, and cools quickly. The magma hardens into solid rock when it comes into contact with either oceanic crust above it or the ocean water when it reaches the surface. You can kind of see what the lava looks like. It looks kind of like a bunch of toothpaste to me. Some of the magma never makes contact with water and solidifies while still hot just below the surface. This volcanic activity slowly adds new crust to the location where the plates are moving apart from each other. Plates that are moving away from each other separate by only a few centimeters a year. So, maybe by this much. So the space along the boundary is easily filled up with upwelling magma. So it's not a huge, quick, fast thing. They move apart very slowly, and that hot magma rises to fill in the cracks. And here's a Midocean Ridge, and you can see all that magma rising. You can play the video. Based on the information you read above, explain what's happening along the Midocean Ridge in the Atlantic Ocean as the African and South American plates move away from each other slowly. So here's a word bank for you. There's some magma involved. There is some divergent plate action. There's some movement. Opposite directions, you could use that word. And this is not the answer. That's a word bank to get you started constructing a sentence or two. All right, I'm going to hit next here. Now we're on page 6. So far, you've investigated places where tectonic plates move towards each other and where they move away from each other. Geologists have classified plate boundaries based on how the plates on each side of the boundary move relative to each other. So we're going to do transform boundaries today, but we've already done convergent, where they come together, and divergent, where they're spreading apart. When two plates move towards each other, the boundary is called convergent. When two plates move away, it's a divergent boundary. There's a third type of boundary that's called a transform boundary. Below is a close-up image from Seismic Explorer showing the plate boundaries at the MidAtlantic Ridge. The blue lines represent sections of the divergent boundary, or they're more kind of green. The pink lines represent transform boundaries, and convergent boundaries are in yellow, but they aren't on this particular map. Transform boundaries are places where sections of the plate slide sideways past each other. Plate material is neither created nor destroyed at transform boundaries, but it does not mean that nothing is happening there. So the plates grind against each other like this, and there's a lot of friction between plates. It's not like they're lubed up with WD-40 or think about giant pieces of sandpaper moving against each other. There's going to be a lot of friction, and so there's going to be earthquakes, there's going to be volcanoes maybe. It's not a nice smooth ride. So the transform boundaries are shown in pink, divergent boundaries are showing in blue, sort of green. What do you notice about the plate boundary that forms the Midocean Ridge? Check all that apply. So transform boundaries connect segments of divergent boundary along the Midocean Ridge. Well, here's transform boundaries, or here's divergent boundaries. And the transform boundaries are kind of filling in the blanks there. Transform boundaries form a zigzag pattern across the Midocean Ridge. It kind of looks like a zigzag to me. Volcanoes form along the transform boundaries. There's not a lot of magma coming up because they're just moving parallel. Earthquakes occur along both transform and divergent. Yeah, we saw a few earthquakes in divergent, and we're definitely going to see some earthquakes in transform boundaries because there's a lot of friction between those plates. Earthquakes are deeper along the transform boundaries than they are under the divergent boundaries. Well, we don't have enough information to really make that decision right at this point. Take a snapshot of the picture showing the plate boundary at the Midocean Ridge. On the snapshot, draw arrows that show you how you think the plates move at the divergent and transform boundaries. So let's take a snapshot. So we know the divergent boundaries are moving away from each other. So that's really easy to draw. I'll draw that in yellow. So these guys, that's moving away from each other. That's moving away from each other. I fill in the divergent first because that's going to help me figure out how the transform boundaries are moving. So I know since this part of the plate is moving this way, that along the transform boundary, the transform boundary is going to move this way. And it makes sense because this part of the plate over here is moving this way. We're going to see that kind of interaction at the transform boundary. Same here, we see this plate moving this way, and we see that plate moving that way, so that's how the transform boundary is going to work there. And if this plate is moving this way here, then this plate's going to be moving that way, which makes sense if you look at this little divergent boundary here. Draw a little arrow there. So hopefully that gives you an idea of how to draw, how to think about those transform boundaries and which direction the plates are moving when they're moving in opposite directions, creating a lot of friction with each other. Southern California is along a transform boundary and as a result has many fault lines where earthquakes are common. The picture shows a lettuce field in El Centro, California, near the border with Mexico, that is shifted after an earthquake. So we see these lines of lettuce, but they're all kind of broken here. The earth actually moved. It looks like at least, well, it looks like almost a foot or a few inches at least, to make these rows of lettuce very different. They're now like broken here. So that's a transform boundary. Here's one row of lettuce, here's one row of lettuce, and now they're offset a little bit because the plates moved. Let's investigate further what's going on at El Centro, marked with a white marker in the Seismic Explorer model so that we can better understand the relationship to plate boundaries. Note that the transform boundary in Southern California connects a convergent boundary to the north with a divergent boundary to the south. So it looks like if we click the key here, here's the convergent boundary. So there's convergence here, and the transform boundary is where El Centro is and where those lettuce fields got all crooked. Transform boundaries are not known for spectacular landforms. They're pretty boring, as you can see in the lettuce field. Based on the earthquakes along the transform boundary in Southern California, what can you say about earthquakes along transform boundaries? Select all that apply. Well, let's see what's actually going on with the earthquakes. Let's map those earthquakes at this boundary here near Central California. Let's cancel that. So let's draw a cross section. I'll do this for you because you can't do this with an iPad. Let's open 3D view here. Doesn't look like those earthquakes are very deep. So transform boundaries, it doesn't look like have very deep earthquakes. They're not making huge landforms. They're just happening and they're shaking the earth. So these are all red dots. Those red dots, I'll remind you with the key, are 0 to 30 kilometers. There's no deep plate subduction like there is on the boundary of South America and the Nazca Plate, where there's a lot of mountain building. So there's no major landforms. There's just earthquakes, and they're pretty shallow. Okay, so here are some plates, and you get to figure out where the plate boundaries are, how we figure out the plate boundaries. I'll give you a hint. There are a couple different ways we can figure out plate boundaries. If you look at just those two things, you'll probably find the plate boundaries quite easily. And then once you find the African plate here, you can find how many plates touch the African plate. And you can go back and you can put the plate boundaries and plate names back in to help you with question 19. So how do plates move and interact? So you get to work with this kind of cool planet here, and you get to find a place where two plates are moving away from each other and take a snapshot, and try to find a place where try to pay attention to what's going on. You get to put continents on here. You get to try making different plates go over and under, and then make sure you set up a divergent boundary, and also make sure you set up a convergent boundary. And the same plate here, you could do a convergent and a divergent plate on number 4, because we'll draw some continents in here. If this plate is making a convergent boundary here, it's going to be diverging from the other plate. So if it's moving towards one plate on the left here, it has to be moving away from the other plate. So that's a hint on how to set up your convergent and divergent boundary for the same plate. And that's the end of activity 3. You can look for other videos where we go over activity 4 and 5. Thanks so much, everybody.